derivation, which is exactly. Yeah. So that's got to come into it as well.
Is it working?
Yeah, I mean, don't have to do that. You don't have to use the R, but yeah, I just use the scope equation. Repetition rate.
We can hear.
Yeah, you're probably using the same things that go into the calculation. Yeah. Yeah. Yeah, I should be able to finish the part.
Okay.
After the talk. You can't do it anymore. Yeah. I have to learn how that goes. I can upgrade the laptop.
Figure I guess I'll at least start off by introducing, yeah, this is Ben. He's visiting from Stanford, and he's going to tell us a little bit about new methods for computing the S matrix and non-matrix resistance.
Thank you, Sarg, and thank you very much for the introduction. So I'll be giving a talk today on, as I say, sort of towards some novel ways of constructing the S matrix non-perturbatively in quantum field theories. I don't assume that everyone is an expert on some of the techniques I'll be talking about, so please, I've tried to make this very pedagogical, but please interrupt with any questions as they come up. I think this is sort of a topic that all of us, is near and dear to all of our hearts, because we're all interested in things like QCD, but it's something that at least in some groups we don't end up talking about as much as I think we should. Okay, so I'll start out with some just motivation. My motivation is that I would like in my lifetime to understand QCD better than we do. In particular, I'd like to imagine that before I die, we'll be able to compute the kinds of things that we actually observe at the LHC. So this is some data. This is data where you're really looking at some particular thing that can essentially be summed up as some ratio of cross sections. This is some inclusive cross section, E plus E minus going to hadrons, but you could look at also any particular E plus E minus goes to PP bar or something like this. If you look at these things around the strong coupling scale, so where QCD is very strongly coupled, you can see that we have a ton of experimental data. That's all of these kind of data points. But we don't really have any way of theoretically computing this. So this is a problem that is kind of the reverse of the problem that we have in a lot of places in physics, where we don't necessarily have data. We're trying to write down models and constrain these models, but we don't really necessarily, it's very difficult to come up with the data. This is an area where the data is very easy to come by, and we even believe we have the right model, but we aren't able to compute things in this model. We aren't able to compute exactly what's happening at these scales. And this is kind of an unsatisfying point to be at. And I think my biggest take-home message of today is that I think this is a problem that's very well worth studying. I think there's progress that can be made, and hopefully I will show you today one avenue that I think is promising. So this problem, yeah.
The mass of rho is very close to the mass of omega, but on your plot, upper plot, it doesn't seem to be close. Rho and omega are split only because
is
I think this is the rho, right? This is the rho. This is the rho prime.
Yeah,
but rho is broad and omega is sitting, so they are on top of each other.
This is the rho prime.
No. Rho and omega is split only because of the
Yeah, but they are the same. One is broad. It's just the way that's different.
Yeah.
No, but the letters are.
Yeah, but
this letter. Yeah, this letter is just.
Peak is the rho.
Yes.
So the peak and rho and omega are in the same place.
This is purely like if I put the rho right on top of the omega, then you wouldn't be able to read the two.
On the side.
Shift, but the peaks are over.
Yes.
The broad
Also, it's a trick of the logarithmic
Ah.
scale. It's also a trick of the logarithmic scale. So you don't
the
put it
scale
in
is
a-
logarithmic,
not the
yeah.
logarithmic scale. They both will be picked at the very same place.
But it seems to be
You
a
wouldn't see
linear.
as much width.
Okay.
So, by the way, this is a good point to mention. Of course, it's not that we have no control over anything at these scales, right? So as you correctly point out, there are understandings of certain resonances.
No,
and
I
things like
just
this, but-
reacted visually
Yes,
because rho stands way left to the omega, but if you
Yes.
look at the table, their masses are nearly the same.
This is true. Yes, correct.
You should put another row on the right. And
Then you can interpolate. Yes.
I'm sorry.
No. Please interrupt. Okay, so here is some recent results that are not mine that I just want to indicate as being a set of promising advances in studying non-perturbative field theories. So these are people that have studied, like you've probably heard of things like the lattice. These are people who are not using the lattice, they're using what's called Hamiltonian truncation, which I will talk a little bit more about today. It's just a new technique for computing basically spectral information in quantum field theories. And I'll talk much more about it as time goes on, so I won't belabor the point right now. But the real promising thing here is you're seeing really genuinely, like this is numerical results computed on like a laptop computer. And you're seeing this is studying phi to the fourth theory in 2+1 dimensions at strong coupling. And you're getting results that are actually pretty good. So
And what is on the vertical?
So this, for both of these, what you're plotting is the mass gap of the theory. So this is at negative coupling where the mass gap actually closes, and you're really seeing that indeed your numerical results have control over this, and you're seeing the mass gap close. This is at positive coupling where you don't have the mass gap close, but there's some nice duality that you can match strong coupling and weak coupling. So you understand that these numerical computations match in the perturbative regimes, and in the very non-perturbative regimes, these two dual theories match each other. And so you're expecting that like this theory is actually computing the right thing. So these detailed results is not what I'm going to talk about today, or not what I'm going to talk about today. I just want to kind of tell you that there's a new tool in the ball game that people have been talking about over the past 5 or 6 years. And the question I'm going to have today is really, how do I take this kind of technique that people have used with some success and stop computing things that are like mass gaps, I mean, although that's really great, and start computing things that are like cross sections and scattering amplitude.
It's
and decay rates.
3D Young-Mills, right?
No, 3D phi to the fourth.
Phi to the fourth.
Yeah.
Okay.
So of course, like eventually you want to get to 4D Yang-Mills. That's very clear. That's a road that's going to take more than a year or two. The one thing that I find really exciting about this is, of course, 3D. Historically, there were a lot of results that people were working on, but they were in 2D. 3D is a lot closer to the real world than 2D is. For example, 3D, gauge theories are significantly more complicated. Any 2D theories are just exactly solvable. There are additional symmetries that pop up. So 3D is really starting to get to, I would say, interesting, realistic quantum field theories.
So Jen,
Yes.
are there arguments about why this Hamiltonian truncation method would work, or is just saying, oh, let me just
There are, yeah,
just applying them to see if the matches no result. So as a check, that expansion happens to work.
good. So there are arguments about how these, like why you expect these things to work. Detailed arguments about convergence, I would say, are not fully under control yet. So it's not really well understood exactly how quickly these methods are going to converge in all cases. I'll talk a little bit more about that at the end, because that's one of the problems that really must be understood before we move to something like 3+1D. Here in the results I'll show you today, I will be thinking about a theory that, although it's not important for these methods, the theory itself is exactly solvable. So I can compare and I can check that my results are correct, although the method doesn't really care about this.
So far, we're still in the stage of
Yes.
following this method to see if it works.
Absolutely.
Right? We're still in a checking stage, right?
Correct. Checking. Well, the checking stage to understand exactly why it's working as well as it does, and then also the sort of how stage of how do you use this method to compute the observables that you're interested in. Okay, the preview, which, at least if I don't get through all of my talk, I will have gotten to this slide, so you can see that we can do something. This is, we're computing in 2+1D, the ON model, so some, collection of n scalars at large n. We're computing the cross section for just 2 to 2 particle scattering in this theory. This theory is exactly solvable, so we know what the answer is. That's this pink line. The black line is a numerical computation that I did on this laptop in like 10 seconds or something. And what you're seeing is that without too much computational power, I'm easily able to reproduce this cross section. This is at strong coupling to order like 1% accuracy. So this is kind of something that my main takeaway today that you should get is like there might be promise in these methods and you should pay attention to them. This is the kind of thing that historically people would not have been able to do. Okay, so the rest of my talk, I've given you some motivation. I want to tell you why is this a hard problem. The specific problem I'm talking about is computing scattering amplitudes. So really those objects of dynamical interest. Why are those objects difficult to compute? I then want to tell you how are we going to do it. Okay, and for the moment, I'm not going to go into any details of Hamiltonian truncation or anything like that. What I'm going to tell you is just imagine that somebody came down and handed you some tablets that contain complete spectral information about a theory. So that's the kind of information that these methods are able to access. And we're going to talk about how do you use that spectral information to reconstruct a scattering amplitude.
Excuse me, may I ask a quick
Of course.
question? ON in 3 dimensions is not renormalizable, right? In the sense that if you start calculating perturbation theory, you will get power divergences. So the theory is dragged to the UV cutoff.
Good. This is at large n, this is not true, right? So at large n, your perturbative theory is completely under control.
Even at large n, why not? Draw a graph and you will see it will have power divergence.
Sorry. Good. Oh, no. Good. Yes.
It's large n, it's renormalizable.
You're correct. You're correct. So sorry, there's a trivial divergence you get. So the only kinds of divergences you're really getting in this theory are sort of vacuum divergences. So you have sort of an overall divergent energy shift, a divergent vacuum energy shift. So if you are not careful about how you sort of define the theory, then you're correct that all the states in the theory, as you perturb with some deformation, your states will all be dragged up to the UV cutoff. However, this is sort of effectively, it's like if you normal order properly, these issues don't arise. For us, that's going to mean, you can see I have this word here that I'm not going to talk too much about, but I'm going to work on the light cone. Working on the light cone essentially removes all the divergences that would plague this theory otherwise. So if there's just one divergence, it's true, but it's kind of a trivial divergence. It affects every state the same way, and so won't matter for us. The hard divergences, which you're totally correct about, are things like logarithmic divergences or something. So phi to the 4th theory, that also has these. That is a problem. People understand how to control this. It won't be relevant for us, but it's understood that there's some renormalization procedure. You have to deal with counter terms somewhat differently in these truncation frameworks, but this is kind of understood. And in fact, some of those papers that I was putting up here, these papers, one of the things that they had to do in these papers was deal with properly regulating and renormalizing these theories. Okay, good. And then I'm going to give you an example, which is the example that I already kind of showed you the results for. So I will compute the scattering amplitude in the ON model at large n. Okay, great. So let's first talk about why scattering amplitudes are hard. So scattering amplitudes, let's remind ourselves what we mean by a scattering amplitude. So typically we start with some kind of asymptotic in state, we end with some kind of asymptotic out state. These are states that are defined in a peculiar way. They're defined as really eigenstates of the full Hamiltonian of your theory, but they have very particular boundary conditions, okay? So the boundary condition is that as I rewind back to past infinity, this thing really looks like two separate plane waves with fixed momenta. And as I fast forward to future infinity, this looks like outgoing plane waves. The usual formulation that we use to compute these things, if you think about doing this in Feynman diagrams, you probably do something like LSZ reduction. And you usually write these things as sort of poles of some time-ordered correlation function. And then you compute that correlation function using Feynman diagrams or something like that. This is somewhat problematic if I want to do something on a computer, because these are very singular objects. You're looking for poles of some kind of correlation function, even if you can imagine computing the correlation function, looking for poles of that correlation function, residues of those poles can be numerically challenging. Another problem is that most numerical techniques, most kind of techniques that we might try to use to compute these things in practice, they're generally on the computer, which means there's something like infinite volume. You don't have an infinite resource computer, so you have a finite volume system. And these asymptotic states, they formally don't exist in infinite or infinite volume. You know, there should be some reasonable way of controlling this. You should be able to take an infinite volume limit, but it's certainly not immediately obvious how to map these onto the kind of states that are probed on something like the lattice, for example. Another huge issue, and this I would say is one of the biggest things that has plagued a lot of previous attempts to look at scattering amplitudes, is that they're really natural objects to compute in real time in Minkowski space, where there is some notion of past temporal infinity and future temporal infinity. They're not such natural objects in Euclidean time. So if you think about what you maybe know about the lattice, if you've seen anything about it, is that it's generally something that you're computing on a Euclidean lattice, and then you want to try to take some Wick rotation. That Wick rotation is not always a very stable process. In fact, in general, it's not a stable process. You're taking something, you know, the path integral converges in Euclidean space, but it doesn't necessarily converge nicely in Minkowski space. So these are just difficult to compute if you're really only ever working in Euclidean time. And then finally, and this will be the least important thing for us today, is there's just very highly out of equilibrium quantities. So even if you have some technique that's able to access things like a thermal state or something like that, that's not always the best state to use to compute some object that really you want to think about basically a vacuum and then two particles coming in, two particles going out, something like this. I can phrase this problem in a very different physical way.
But before you go,
Yes.
like, isn't it true that for engineering theory, you wouldn't even know what your asymptotic states are, right? Because, like, who knows? Like, who would knew, right, that the QCD has hadrons?
Good.
Look at the just the Lagrangian, right?
So this is true, but this problem I am actually less bothered by, because I have more ability to access something like this even in Euclidean space. I can look at something like you know, one can identify the low-lying spectrum of QCD with the lattice, and that's great. That's a huge, tremendous success, and I don't want to diminish that. But then actually trying to take those states and scatter them is not something that's so easy to do there. So spectral information is something we have access to in some of these theories, but taking that, and if you study quantum mechanics, you would think spectral information is all you need, right? You did your quantum mechanics problem, and the problem was always solved for the eigenstates of the Hamiltonian. And once you've solved for those, like, you're done. Here we need to kind of go a step beyond that. Even if we have the eigenstates of the Hamiltonian, how do we actually take that and look at this kind of dynamical information? And that's not a completely trivial process. That's what I'll talk about today. I can phrase this problem this in a slightly different way that may be familiar to some of you, I'm not sure, which is sort of the old Lippmann-Schwinger equation. This is sort of what we mean by asymptotic states. So what is an asymptotic state? I say an asymptotic state, well, I want it to be an eigenstate of the full Hamiltonian. So I have h times some psi is e times psi. I take that Hamiltonian and I split it up into something like a free part that I say is exactly solvable and some perturbing potential. I can rewrite this, and I can just say, okay, I can get an equation for psi that formally looks like this. It looks like kind of 1 over this operator, E minus H naught, times V times psi. And then when I demand that I want my full theory eigenstate to look something like a free theory eigenstate when I take the potential to 0. So this is kind of our identification of quantum numbers or something. You know that quantum numbers, like, there's meaning to talking about the quantum numbers of a proton and thinking about that in the same way that you might think of like valence quarks or something like that, even though the actual proton is much more complicated than that. When I do this, first of all, I get this piece that just looks like the free theory state. And then I also get this piece. And in particular, this has a pole, right? So E is a constant. H naught is something with some continuous spectrum of eigenvalues. And so there is some pole to this operator. This operator is not well defined. I need to insert something to resolve that pole. That's, you know, this I epsilon. And when you work this out, you find that you have two choices there. One of those choices corresponds to the boundary condition of sort of a future infinity out state. One of those choices corresponds to a boundary condition of a past infinity in state. And it's really important because you think like two plane wave states, something like, a proton with this momentum and a proton with this momentum, there ought to be two different kind of states that can correspond to, either an out state where these are in the future or an in state where these are in the past. And then the S matrix is kind of just taking the overlap of these states.
Excuse me, maybe I will interfere interrelevantly, but in 2 dimensions, this model is solved exactly. At Lagian, it is solved exactly, and
Yes.
at n equal 3, it is integrable and also,
Yes.
and then O3 is also solved exactly. And there in the exact solution, you say that the spectrum physical spectrum has nothing to do with what you see in the Lagrange, right?
Yes, okay.
And you want to develop a perturbation theory starting from what? From three?
So there's no perturbation theory
Okay.
here. Yes. So the Lippmann-Schwinger equation is exact, right? This is an exact equation. Now, solving this equation is generally difficult. So the way we usually solve this equation is we develop perturbation theory for it, but this equation is exact. Okay. The point is we are eventually going to want to put this theory on some kind of computer. We're eventually going to want to solve this problem. And once I discretize the system, the spectra that I get are no longer continuous. And so this pole is just gone. It's generically quite rare for the free theory, the sort of free theory eigenvalue to be exactly the same as a full theory eigenvalue. And so I just no longer even have any notion of these asymptotic states. And that's true basically regardless of my discretization procedure. Okay. This may seem like a pretty dumb problem, but it's actually kind of serious when you think about what this means for defining the S matrix. We have to think carefully about exactly how to define that properly. And we're going to have to find a way to avoid ever dealing with poles of these functions, because these functions aren't going to have poles in the proper places. Okay. We've already talked about this somewhat, so I'll breeze through this slide quickly, I hope, which is just, I want to do like fairness to the wider literature. There are other techniques that people try to use to control things like scattering amplitudes. One of these is the lattice. So the lattice there's two different ways that you can imagine doing this. One is called Lucher's method, one is called HAL-QCD. I'm happy to talk to you much more about these things. I think it's probably not the most relevant thing now, but you can talk to me afterwards. The main takeaway message from these is that really they're only good at computing the elastic part of the amplitude. And roughly that's because the elastic part of the amplitude is nicely encoded via the optical theorem in other properties that can be computed in Euclidean space. But we know that there are many observables we would like to compute that are inelastic processes. And so I would say this is a really great set of techniques. It's not, I would say, fully general, and it would be nice to understand more. Another is there are just various kinds of techniques that people try to use by using like unitarity bounds or analyticity structure of amplitudes. These generally result in placing some tight bounds on the amplitude. Sometimes those bounds are so tight that you can think of it as really computing the amplitude. Other times those bounds are very wide. It's sort of well known that there are theories that lie very far from certain unitarity and analyticity bounds. So these are all great tools. I don't want to diminish any of them, but I certainly am not satisfied that we have a nice full recipe to start with a theory Lagrangian and end with a general spectrum. Okay, are there any questions before I keep going? Because now we're going to get a little bit into the weeds for a while with some technical details, and then we'll get back to results. So my big question is going to be, let me take it for now as a fact that I have access to spectral information of the theory. I'll talk about how to get that later. Let me suppose that I have sort of full knowledge of the eigenstates and eigenvalues of the full field theory. How can I compute the scattering amplitude? Well, the way that, like one way you might imagine doing that, of course, these are actually eigenstates of the theory. But the problem is these eigenstates have very particular boundary conditions, and those are very difficult to construct. That's generally not what we have access to. We probably have access to something like approximate eigenstates of the theory in a finite volume box. So that's what we should really be thinking we likely can work with. One thing you might imagine doing is saying, okay, let me just start with something like the LSZ reduction formula. Here, I've only reduced out 2 particles instead of all 4, but it's the same formula you know and love. So I've expressed this kind of scattering amplitude as a Fourier transform of some time-ordered correlation function, poles of that time-ordered correlation function. And something you could imagine doing is saying, well, look, if I have complete knowledge of the spectrum of the theory, I can just insert complete sets of states into that object, and I can try to evaluate all these correlators. And if I can evaluate these correlators, I can compute this object. As an aside, of course, one of the reasons that I only reduce 2 of the particles, that I leave 2 of them sitting in these in and out states, is because 1 particle states are the only asymptotic states we have easy access to, because a 1 particle state just looks like a 1 particle state, whether it's coming or going. So that is the one kind of state that we generally have access to with any numerical technique. The big problem here is as soon as we've done this properly on our computer and we've tried to discretize, I'm just telling you the same thing I've told you a few times before, is we're going to have this correlation function. This correlation function is supposed to have poles. After I discretize, I'm only going to have some approximate poles. I'm then going to multiply by exact zeros on shell, and this is going to be a very numerically ill-posed problem. So you can try to do something like this, and you just get garbage results. You never are able to compute anything that looks interesting. So the problem we see is that these poles and zeros do not properly cancel, but that also immediately suggests the kind of solution that we're going to want, which is where are these poles and zeros coming from? They're coming from the equations of motion. Right? That's really just accounting for the propagation of the asymptotic states as they run off to infinity or come in from infinity. So roughly, we understand we just want to use the equations of motion to deal with these objects, and that's exactly what we're going to do. So the equations of motion for a quantum field theory, the way that they manifest themselves is these sort of Schwinger-Dyson equations. So the equation of motion for like a classical field theory, that's just the variation of the action is 0. In a quantum field theory, we find that the variation of an action is almost 0. What do I mean by almost 0? I mean I can put it into any correlation function, and this thing is exactly 0 up to contact terms. So terms where some operators are coming together and hitting each other. Okay. This object, you can massage a little bit, and what you can find out is that by using these equations, I can rewrite this correlator, which is the one that I was just interested in, as some object that's written in terms always of currents. Okay, so the currents are, if you remember, I take the potential that I've inserted and I just take some derivative of that with respect to the field. And so I understand that I can write this object in terms of some current correlators and then some contact terms where some two points hit each other. This is really nice because all of these objects, they no longer have any poles and zeros canceling. So these are all manifestly smooth when all particles are on shell, which means I now suspect I will have a much easier time discretizing the system and then reconstructing what this correlator actually looks like. Okay.
Excuse me, isn't it true that what you wrote as a transition from P1 to P4, it's a green function, right?
Yes.
It's 2-point green function, right?
But in some background, yes.
Of course, if you multiply it by inverse green function, like box plus m squared, of course you get, you might get a contact term, but other than that, it is 0. It's not interesting. What if you consider a 3-point function?
Well, sorry.
This would be a scattering amplitude. This
No. Good. This is right. So where did this object come from? It came from some formula like this, right? So it's this object here.
Yes.
This is a 4-point function.
Okay.
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 It's you're right that there's some Green's function looking thing in there, but it's in a background, right? It's in a background that's not the vacuum background. It's in a background of external particle states, P1 and P4.
Okay, so
you
put 2 of the particles,
Yeah.
so it's not in the vacuum, T
Yes.
product, but with average between scattering
Yes.
P1 into P4.
Yes. So this is a 2-to-2 particle scattering process.
Yeah, but how do you calculate in Euclidean path integral this amplitude?
So one, I will never be using Euclidean space today. I will only be using Minkowski space. And then 2, I mean, what I'm about to tell you is sort of how do I evaluate this exact correlator? That's where we're trying to go.
Okay.
So what we did is we just rewrote this correlator, which looks poorly behaved. It looks like some kind of pole of zero canceling, and we rewrote it in terms of some objects that are smooth. These objects we should be able to approximate much better. I want to emphasize that the thing that I'm telling you today is fully non-perturbative, but to help you gain intuition for this formula, I'm going to show you a kind of diagrammatic intuition behind what's happening. So what I started with was some object that looked like this, and this was really an object that was computing the general, like the general scattering amplitude. And all I'm saying is that in some theory, let's take 5 to the 4th theory as an example, any diagram that I can write down on this side looks something like basically falls into one of two categories. One possible category is these two external legs come in and both interact at a vertex. Okay. If that is the kind of thing that I'm looking at, well, J, for a potential that's like 5 to the 4th, J is like phi cubed. So this is really a correlator that now looks like an external P1, an external P4, and some insertion of a 3-particle interaction. So creating or destroying 3 particles. The other possible way that this diagram could look is that both of these two external guys could come in and interact at the same vertex. And that's really this J prime interaction. So that can only happen if they're interacting at the same space-time point, which is why it's a contact term. But you can kind of see how this factorization works. Okay, is that clear? I have a kind of cutesy diagram for this, where this guy looks like a blob. I can rewrite him as either a happy kind of guy with cat ears here, or a guy with a little birthday cap. And both of them are very happy because they're easy to compute. Okay, so now we have our tool. We just kind of take this, we plug and chug. So we are going to take that JJ correlator, this guy. We're now going to insert a complete set of eigenstates between these two J's. And we're going to just do the kinematic part of the integral. So we're going to do the Fourier transform. When I turn that crank, I get something that looks like this. So my scattering amplitude, remember there was a time ordering, so there will be 2 contributions coming from the 2 possible time orderings. The scattering amplitude can be written as something like this. There's a J correlator, where what I've inserted in the middle is some complete set of eigenstates, which have some eigenvalues, some invariant mass eigenvalues, and some momenta. There's one for the ordering, for one of the time orderings, there's another one for the other time ordering. The Fourier transform, I can do that Fourier transform. It's purely a kinematic integral, and that is going to turn out something that looks vaguely like a propagator. So it has some invariant mass of the intermediate eigenstate, and then either S or T, that's the Mandelstam S and T, that sit here. So there's kind of some propagating on-shell intermediate states. And then finally, I have this contact term that's sitting around, that's still there. And the power will be that if we know this guy and these guys from some kind of non-perturbative technique, at least some approximate version of this guy and these guys, then as long as we can compute these correlation functions, which are now easy objects to compute, that's the inner product of some operator between 2 known states, we'll just be able to compute everything here, add it all up, and get an approximation to the scattering amplitude. That is the takeaway message from today, and that's just what we're going to be doing. And I'll show you results for that. For people who have studied these kind of things before, especially more formal quantum field theory, this may look familiar to you. It may look somewhat like a dispersion relation. That's not a coincidence. So this kind of is a dispersion relation. If you are not familiar with this, don't worry about it. It's not that important, but I just want to make that connection for those of you who have thought about this stuff. This formula, like the one way that you can compute a scattering amplitude, if you have a scattering amplitude that has some nice complex analytic structure, is you can exploit the residue theorem, or maybe it's not the residue theorem, I don't know, one of these complex analysis theorems to say that the scattering amplitude at any one point can be written as the sort of a contour integral around that point. I can then blow that contour integral up to the entire complex S plane. And the only things that I'm not allowed to do is cross the branch cuts and poles that I'm dealing with. So generally, you have some way of writing a scattering amplitude as some integral over the positive S branch cut. This is corresponding to like 4 particle, 5 particle, 6 particle, 2, 3, 4, 5, 6, et cetera, intermediate states. There's a continuous spectrum here. There's also a continuous spectrum that can sit at T that's sort of the same states, but by crossing symmetry. And then sometimes there's some poles or things like this. There might be some subtraction terms. Those are popping up here, and we are actually seeing a formula for computing those subtraction terms. Okay.
It's called the dispersion representation.
Yes.
Lambda.
Yes, exactly. Good. So our big picture, we started with an object like that. We used LSZ to turn it into an object that looks like that. We used the equations of motion to turn it into an object that's much smoother, no longer has any poles. And then, and here is kind of the only approximation that we're going to make. We're going to insert this complete set of eigenstates that is kind of an approximate complete set of eigenstates. And then we're able to evaluate all of those guys exactly. Okay, so the our path is clear. The only thing we need to do is understand what that approximation is going to be. That is what we do on the computer. And the basic idea is quite simple. We just want to discretize the Hilbert space of the theory. The Hilbert space of a quantum field theory is some very complicated large space. We want to discretize that in some clever way, and clever is doing a lot of work here. Once we have that discretization, we now have a finite dimensional kind of truncated Hilbert space. We want to just construct the full theory Hamiltonian for this truncated set of states. And this is now a finite dimensional matrix. Okay, we can generally compute all the matrix elements of this matrix without too much difficulty, although of course we do have to choose the way that we write down our truncate, or we have to choose the way we truncate our Hilbert space to make sure that computing these matrix elements is possible. But we now have a finite matrix, and we can just numerically diagonalize that matrix to get some set of approximate eigenstates of the theory. There's a lot of work happening in this quote unquote good, and that's where all that progress that I was mentioning at the beginning of the past 6 or 7 years has gone. It's in finding clever ways to discretize the system such that the matrix elements are still calculable, and the theory seems to converge reasonably well.
Wait, Chad,
Yes.
so these eigenstates that you're computing approximately and then inserting, when you wrote them down, when you actually inserted them, they looked like one particle, like asymptotic states. But
No, sorry, these do not look like one particle asymptotic states at all. I mean, there will,
as some like momentum eigenstate.
I just wrote it with like any state that I have that's some horrific mess of stuff, it's going to have a few kind of things that I can associate to it. So the things that I wrote it actually with, I wrote it with some, let's call it mu I squared, and then some momentum. So as long as my, like, let's say I start with a free theory that's well understood, easily under control, it's a trivial theory. And now let me deform that theory with some operator that may be very strong, like some strong coupling theory. As long as that operator doesn't break translation invariance, momentum is still a good quantum number. And so I can index all of these states with momentum. And then this is really code. This is code for something like E squared minus P squared, right? Some invariant mass. This is a good quantum number, that's this. And then this is just whatever the eigenvalue of the full theory Hamiltonian is. So after I diagonalize that big matrix, I'm going to get a bunch of states, and what are the eigenvalues of those states?
Okay, but you're doing this within a finite volume. So like
I mean, of course, there's some effective finite volume, but you're deliberately doing this in a way that nicely preserves translation invariance. Yeah. So not like you're not doing this on a lattice where you have a really clear finite box. You're trying to regulate your theory in a way that nicely preserves all these symmetries. So good. The results that I'll show you today, I'm always going to use this kind of light cone conformal truncation, which people have worked out over the past 6 or 7 years. It's not the focus of my talk because it's not the method that we're developing here. We're developing how to connect these kind of results to scattering amplitudes. I'm very happy to talk much more about that, just probably afterwards offline, because I don't have enough time to go into full depth about how these techniques work and then also show you results. But the key is all this is a very clever way to do exactly this, to come up with some approximate set of eigenstates. And I want to emphasize that if you come up with some different good way to get some approximate set of eigenstates, that's completely fine. I will happily jump on board with that. You can use exactly these same techniques to compute a scattering amplitude.
Would you say that, say, chiral is some sense that, because you say, okay, my new squared super large, I will just throw away from theory and I will put all my ions multiplying states in S channel, T channel, and I calculate, and I will have the sort of a limited range of applicability because of my term. So it's in some sense that.
I would have to think. I do. So one thing that's related to your question, but that I don't have a good answer to, is I suspect there's a very close mapping of like any effective field theory into this language. It's not completely clear to me what that mapping is. Like.
I'm just trying to say that the light on truncation is one, right? But another one is.
Oh, sure.
Just
Yes,
say
yes.
Any states I will
Yes.
ignore them, right? And then that.
Yes.
Also a simplification.
Yes, I agree. Okay, so now we come to the example. I'll tell you a little bit about this theory. This theory is the ON model in 2+1D at large N. I'll tell you just enough about this theory to let you understand the results that we're getting. The details aren't very important. The only reason I'm choosing this theory is because it is one of the few theories in 2+1D where I know the exact answer from some separate tool. And so I just have something to compare my results to. Okay, there's nothing special about the ON model that's demanding that, oh, you could only use these techniques because the ON model is exactly solvable. It's just when you're starting out, you really want to know that you're getting the right answer. Okay. So what is this theory? This theory is a theory of n massive scalar fields related by some ON symmetry. So I have, their masses are all the same. And then I have some interaction. It's a kind of phi to the fourth interaction. The amplitude that I will be looking at is just the 2 to 2 particle amplitude. And this, you can see that there's kind of a flavor choice I have here. So I can have two particles in the in state, 2 particles in the out state. Each of those can be a different flavor. At large N, this amplitude is exactly known. This amplitude splits into kind of 3 different pieces depending on which flavor choice you take. Either the two starting guys are the same, the 2 final guys are the same, or some crossed symmetry version of that. And then this amplitude is known exactly. It should be clear that this amplitude is not like a perturbative amplitude. Like this thing has some complicated logs and things like that our technique is going to have to reproduce. Fundamentally, the reason that this theory is exactly solvable at large N is just because at large N you can kind of factorize many of the diagrams away, and so the amplitude reduces to diagrams that look like this, kind of bubble chains, either in the S direction, the T direction, or the U direction. The non-perturbative nature here is really that you need to resum an infinite class of these bubble chains in order to get the final amplitude. Okay, and sort of intuitively, that is what our truncation is going to be doing for us. It's going to be taking something that it's some many different classes of interactions and resumming them all together to get the full non-perturbative result. Okay.
Excuse me, if you just forget about numerical calculations and light cone and use 1/n expansion, ignoring linear divergences, you still have factorization. What else do you need in order to write this type of web?
Good. This, I'm not saying light cone is doing this for you. I'm saying this amplitude is exactly known. Amplitude is exactly known for this reason. It's known because you can do this large N counting effect. Yes.
That's exactly the chain which you depict.
I'm choosing this deliberately because I want to compare to something with a known answer. Okay. Like I'm doing, I'm trying some new technique. If I try this new technique in a theory where I don't know the answer, then how do I know if I'm getting it right? But here I'm going to try it on a theory that I know, and then I'll go and try it on a theory that I don't know and make some prediction.
Is that expression only true for large N?
Yes. This is the leading order in N.
This logarithm is the denominator because it's a sum of the geometrical progression.
Yeah.
You have one loop has an imaginary part. It is logarithm which has an imaginary part if you discard possible linear divergences. This is logarithm. And you sum It's 1 plus x squared and so on. And then it goes in the denominator.
Okay, so we see that these, there's kind of 3 different choices we can do here. What I'll call this kind of the S flavor amplitude, the T flavor amplitude, and the U flavor amplitude. Of course, they're related by crossing symmetry. But what I will do right now is I will just pick one. I'll pick the S flavor amplitude, and I will compute it using this this technique that I just showed you. So what do I do? Diagrammatically, it's that S channel bubble chain that I just showed you. In truncation, the thing that corresponds to, the fact that I'm at large n, it does simplify my truncation job a little bit. It means that I can just use 2 particle states in the flavor singlet sector. Now these 2 particle states are not diagonal. Like if you write down all the 2 particle states in the free theory and then you deform with this full interaction, the matrix is highly non-diagonal. You really need to do some complicated non-perturbative diagonalization to get it. But it's just those are the states that are entering into this. So I've written down the exact same formula you saw earlier. The only thing that I've done now is I've added flavor indices here. There's some flavor index choice here. And when I add those flavor indices, I get some simplification because at large n, this contribution here, the flavor indices match up. And so I get something that's at largest order in n. This contribution here, the flavor indices don't match up. And it turns out this means it's suppressed by 1 over n. This is just a detail. It's not very important for the method we're describing, but it's just kind of how the calculation runs. And then this guy, it turns out the 1 particle states at large n are just not renormalized at all. The 1 particle states remain exactly 1 particle states. That is a peculiarity of working on the light cone, which is very helpful. But yeah, so we can compute this exactly at large n, and then these guys we can compute using truncation. Okay, when I do this, there's kind of one last discretization problem that if you're looking at this formula, you might worry about, which is I have these propagators that sit here. And these propagators, what it is it's a sum over many intermediate states. These have some non-perturbatively calculated spectral information, so some particular energies. And at each one of these intermediate states, there's a pole, right? There's a pole that sits here when when S, the Mandelstam S is equal to the invariant mass to that state. So intuitively, what's happening here is you're kind of writing down, you're very used to this idea when you think of something like a resonance, right? You have some 2 particles that come in, they make some long-lived resonance, and then that resonance goes away, and there's some pole associated with that resonance. Here, I'm getting just a whole bunch of on-shell poles that are corresponding to all the different states, that would be in the continuum. It would make up a branch cut of the amplitude if you were to write down the amplitude in that language in the continuum limit. When I discretize, I just get a whole collection of poles. Each of those poles looks a little bit messy, but it should also be clear that that's not a big problem, right? Because all that's happening is, when you discretize, you get like right here on the real axis. It's the bad one. On the real axis of the complex S plane, you've gotten a whole lot of poles that sit here, but you know that those poles are really trying to reconstruct a branch cut. And so all you're really supposed to do is kind of smooth over a couple of them. If you want to look at the amplitude right here, then you're supposed to smooth over the many, the many poles that lie right next to you and take the amplitude that way. And the only requirement is that your poles are closely spaced enough that they're spaced much more finely than any macroscopic features of the amplitude. Okay, good. So that's basically equivalent to taking a finite epsilon here. If you take a small but finite epsilon, then what you will do is you will naturally smooth over these many poles and you will recover something that's numerically stable. Okay, so with all of these different ingredients, which I mean individually or sort of macroscopically, it may seem complicated, but each of these individually is very easy to do. You just plug it onto a computer. This is kind of one line of code to do this smoothing. The diagonalization matrix is, a few lines of code, things like this. You get results that look like this. So this is the 2 to 2 scattering for this S flavor amplitude that we just talked about. I'm looking at the real part of the matrix element and the imaginary part of the matrix element. I'm looking at quite strong coupling. and you're getting kind of percent level residuals. So the pink curve on both of these is the true exact theory prediction that we just saw. And the black curve is what the numerics spit out. And this takes, 10 seconds on this computer. So it's not very computationally intensive to get these kind of results. Good. I think I'll pause for a moment here for any questions, but this is kind of the big upshot of all the work we just did, was to get plots that look like this and see that indeed you're reproducing these features pretty faithfully, even the sharp features right at threshold, things like this. You're capturing them quite faithfully. Of course, this dashed line here is the threshold, sort of in Mandelstam S equals 4. Below the threshold, of course, there's no physical amplitude here, but this is kind of the amplitude related by crossing symmetry. So I plot that too. Are there any questions here?
Can you explain the choice of Imax and dot max? What do they match
These are truncation parameters. So this heuristically is corresponding to kind of if you want kind of the intermediate spin, like I'm including 2 particle states. Those 2 particle states have kind of a spin eigenvalue associated with them in the free theory. When I go to the full theory, of course, all these states get mixed together and whatnot. This is kind of corresponding to the maximum intermediate spin included in those states.
That's the truncation you made.
Yes. Yes.
Intermediate set.
Yes. Exactly. So if I wanted to get more precise results, I could take these guys and go to larger values. This Imax is it's sort of corresponding to in doing this, we at some point have to write down a kind of UV cutoff for the theory. Like we have to regularize this theory somehow. The way that we do that is we regularize the theory with some basically hard UV cutoff, and then we within that UV cutoff basically split up into a bunch of different energy bins, and this is kind of the number of energy bins that are in that. So this there's one other parameter that's not actually written here. That's basically what is that UV cutoff. That's not a truncation parameter per se. It's just kind of a regularization parameter. You just want to take that UV cutoff to be very large compared to whatever scales you're looking at. This is kind of controlling how big that UV cutoff is relative to the threshold if you want your bins at threshold to be some particular degree of fineness. I should say, of course, I want to compute this amplitude at threshold because that's where the interesting features are for me. So I have deliberately chosen my truncation. I've deliberately chosen my discretization to favor states in the IR. Okay. If I wanted to look at a feature that we're sitting way over here, then I could have chosen my states deliberately to, more closely approximate states at that larger invariant mass. Okay. So it's unlikely that the thing you're going to want to do is discretize one time and compute all states. If you're doing something at the LHC, you're not going to want to compute all states over like 3 orders of magnitude in energy. Instead, what you're likely going to want to do is say, I want to look at this particular feature that I know is happening somewhere around this energy, and I want to specifically decide, my truncation parameters such that they favor states around that region. And this is just the reason this works is a form of decoupling. Like states at much higher energies and much lower energies generally aren't affecting.
Yeah, but that's the hope, right? You hope you.
That's the hope. Yes.
Smart bases that have this.
No, you're correct. Like yeah. Yes, this is these I think it's an unfair comparison to compare these to like the lattice in this sense, because the lattice has 50 years of work behind it, and this has 6 or 7 of these very recent advances. But yeah, it's absolutely true that understanding convergence for these theories and being able to put that on a very rigorous footing is quite important, and that's something that people are thinking about right now. Yes.
So when you get very, very close to the threshold, you obviously start disagreeing because you're going to get a finite answer.
Yes.
But is it like how close does that happen? Is it like epsilon or?
Good. Yeah, this is basically, I chose some smoothing scale, and this is the smoothing scale. And so you know how when your results are going to start breaking down, because you see these poles, right? These poles are the information you get out. That's the spectral information about the theory, where are the eigenvalues of the theory. And so you also see the spacing between those poles. And like, you know that when you are getting to regions that are within the spacing of those poles, your result is not going to be accurate anymore. So as soon as you're kind of there's a spacing of those poles right at the threshold. As soon as you're within that, you say, oh, I don't trust my result. No way should I.
If you increase these truncation parameters,
Yes.
the poles get
Yes.
closer, and so you can go.
Yes. And in fact, like, I chose these to also like populate a large region here because I want to be able to show you a nice plot. But if you told me that the thing that you really wanted to know was exactly the threshold behavior, then you could have done that. You could have said, okay, screw everything way up here at S over M squared of like 20. Let me just focus in at S over M squared of smaller. Of course, you need some states up here because like they still contribute somewhat, but you can do much better by really focusing in on places that you care about.
Excuse me, may I ask a question? Could you please explain, because I realize I don't understand, how you generate a mass gap in three-dimensional or 3ON model? It's
Well, sorry, there's an
mass
explicit
gap.
mass.
How do you get an independent mass gap?
Sorry, there's an explicit mass here.
Yeah.
Yes. So there's just a mass gap in the theory from the beginning.
You put it from the very beginning,
Yes.
but then it's not called the ON model. The ON model is d mu n squared with the
Okay,
condition
so-
n
so-
squared equal to
How
1.
about massive ON model? Is this?
ON model means
I mean,
something.
so look, to be clear, the actual thing
It's
that I
my
analyzed. Yeah,
theory with n fields. That's what that
Fine,
is.
fine. So to be clear, the actual thing that I do here is this is the only interaction that I have in the free theory. The mass is also treated as a deformation, but I'm just saying I deform with the mass as well as this company.
No, of course,
Like I have two
this
deformations.
theory is okay in 3 dimensions. This is a renormalizable theory in 3 dimensions.
Yes.
I had in mind what other people call the ON model, d mu n squared with the condition n squared equal to 1. What all condensed mean, if you ask
Oh,
any
sure.
condensed
Okay,
theory
sure.
person, that's what he would tell, or
Okay.
she would tell you. This is scalar field theory and fields with ON symmetry, but okay, it has some other name. Result.
Okay,
I don't-
massive ON model. Oh, is this more? I mean, there is an ON symmetry, which is which is important for us.
Yeah.
Okay, yeah, there was
I
a.
also wanted to ask about the mass. So
Okay.
is it important somehow in your computation because at some point you say that your formula is kind of similar to this dispersion relation, right? And the dispersion relation, the mass gap is kind of important, right? Because otherwise the
Good. I would say no. I don't think that it's really important. Yeah. Certainly, I could compute these kind of plots without the mass deformation. The theory is more interesting with the mass deformation. So if you don't have the mass deformation, then the truncation calculation becomes more trivial. So this is actually a much more non-trivial test. If you like roughly, this is technical details that I'm much more happy to talk about offline, but kind of the mass deformation is mixing states in a different way than the phi to the fourth deformation. And so the matrix that you construct and diagonalize with both is actually more complicated. Yeah. Okay, I'm fairly low on time, so I'm going to mostly skip this next part, but just to say there, like you can compute the T-flavor amplitude in a very similar way. Of course, the T-flavor amplitude is related by crossing. So once you know the S-flavor amplitude, you also know the T-flavor amplitude, but it is kind of instructive to see how the T-flavor amplitude is computed with truncation. You need different states. Instead of having the 2-particle flavor singlet states in the intermediate area, you actually have some 4-particle states that you need to care about as well. I won't get too much into this. Unsurprisingly, you reproduce the T-flavor amplitude extremely well. It's just that part of the S-flavor amplitude, but continued over to the left. There is some very small deviation. This is actually purely a UV cutoff effect. So this is a systematic effect. It's not a statistical effect. It comes from the fact that the theory has a UV cutoff. We've had to regulate it. If you want to reduce this effect, then you just include states that allow you to push your UV cutoff higher. It's also much smoother, like the truncation calculation is much smoother than it is for the S flavor amplitude. Intuitively, that's because you're computing the S, by crossing, you're computing the S flavor amplitude all the way over here, which is very far away from all these poles. So all of the messy pole effects are canceling out. You're just far away from them. Good. Something that I find really interesting and exciting about this technique as well is you can look at the full complex S-plane. You can look at the full complex amplitude. There was nothing in the formula that I showed you that demanded that the Mandelstam S and T that we take be real. So I can actually take them to be complex. There's some mild subtleties with exactly the deformation I'm allowed to take. So because I left P1 and P4 as external states, I'm not allowed to deform those particle energies. But deforming particles 2 and 3, those energies is completely fine. I can do that. I can go to complex Mandelstam S, and I can reconstruct the full complex amplitude. So here you're actually seeing this. What I'm plotting is the phase of the amplitude, and what you're seeing. This is the truncation calculation. There is the threshold, and I'm reconstructing basically the discontinuity across the branch cut. I'm seeing that the phase on one side is positive, the phase on the other side is negative, and indeed. There's a jump right as I go across the positive real axis. One reason you might care about this, even if you're not interested in any kind of formal field theory stuff, is because convergence tends to be much, much better away from the real axis, intuitively because there's all these poles that sit right on the real axis. And so you get a little bit farther, a little bit away from them, and convergence becomes very good. In the past, so what this is, these are residual plots. So residual plots for the absolute value of the amplitude and for the phase of the amplitude. And you can see that like here, the absolute value of the amplitude is always like the residual is less than 10 to the minus 3, basically everywhere in the complex plane. For the phase, it's even better, less than 10 to the minus 4, less than 10 to the minus 5. So it's possible, though this is not yet really done, that one could really go to a region where convergence is extremely good, carefully construct the amplitude there, and then analytically continue back to the real axis to enhance convergence. This has been done for some problems, using truncation data, but not yet for scattering amplitude. So this is something that at the moment is still a little bit speculative for this problem, but it's very promising at least that we have good convergence throughout this plane. I'm almost done. One other big question that you might have is what happens in a more complicated theory, and this is kind of where I'm getting to, where do we want to go in the future? The complex amplitude is an important promising thing for that, because you can imagine, like, let's talk about a theory like QCD. QCD has a ton of bound states, resonances, things like this. Those states manifest themselves as analytic features in the scattering amplitude. They manifest themselves as poles that sit off the real axis, some unstable resonance pole. It's possible that with these techniques, you could attempt to reconstruct those poles and get better information about, exact properties of particular resonances or things like that. It's unclear though, because generally many of the most interesting features in the full complex scattering amplitude of some theory are hidden on higher sheets of the complex S-plane. And with the way that we constructed it here, we're always just constructing these specific poles that we're kind of always stuck on what they call the physical sheet. And so some of these, some of these properties may be less accessible. In particular, like in the continuum, you have some branch cut. I'm allowed to kind of go through the branch cut. I'm allowed to continue around and through the branch cut to get onto a higher sheet of the sort of complex Riemann surface. But here we don't have a branch cut. We just have these discretized poles. And so it's not as clear whether I can continue through that in any meaningful way and end up on some higher sheet where I might be able to see a pole. Okay, with that, I'll basically conclude with looking forward. And this is my pitch for like, where can we hopefully go? Not next year, not the year after that, but maybe not 20 years from now, maybe sooner than 20 years from now, right? So maybe this is a time scale that's accessible to us. Again, my hope before I die, I want to understand QCD better than we understand it now. And there's kind of a couple of things that should be very obvious that we don't have from what I just showed you today. And I just want to go through kind of which of these seem like big hurdles and which of these seem easy. The first one is fermions, okay? And the reason I bring this up is because it's not a problem. Fermions are completely trivial for these techniques. They have posed no computational complexity at all. And this should be contrasted with like the lattice, where there are many, many fermion problems, like sign problems, things like this, that plague the lattice and plague lattice realizations of things like QCD. So that's a really great thing about these techniques that I haven't talked about today, but that is true. Going to 3+1D though, this is going to be a little bit harder, and it's harder for a subtle reason. The reason is that basically any interaction that you want to look at in 3+1D is marginal. And typically not even just marginal, they're actually mostly marginally irrelevant. This is at the moment a problem for convergence of Hamiltonian truncation. There hasn't been much work in it, but it you know, sort of so far people have not been able to get really good convergence for marginal interactions. Intuitively, this is because roughly what these techniques are doing is starting from some, this one's bad, is starting from some, you know, UV fixed point CFT that lives up here, deforming away from that in some direction, and then flowing down to, you know, the theory that you're actually interested in the IR. Okay, this theory is generally exactly calculable in. So this is like our free theory, where, you know, there's no mass, there's no coupling at all. This theory is typically easy to calculate in. That's how we are able to calculate these exact matrix elements. Then adding our deformation, so adding the interaction to the theory, causes us to flow down towards this theory that we're interested in. And convergence is going to be best if this flow is fast. Okay, this flow is kind of quick in energy. For a very relevant interaction, like the interaction we were working with today, this convergence is fast. Sort of, we didn't need that many states. We flow towards the IR theory fairly quickly. For a marginal theory, that flow is slower. It takes longer to get there because your interaction is marginal, and so you know the flow is logarithmic. Understanding this, too energetic. Understanding this properly is kind of an open problem. There hasn't been a lot of work on it yet, but it's something that needs to be done. Another thing that will be very relevant for QCD is kind of scattering bound states. You never scatter a fundamental state in QCD. You scatter something like pions or proton or something like that. These are states that exist in the theory. Absolutely, we can see them in truncation. We can see them. We can see a bound state. That should be no problem. But it will require some generalization of our JJ formula, because the Schwinger-Dyson equations, the equations of motion, aren't as simple for a bound state, you know, where you have to write the interpolating field as some kind of composite operation. And finally, gauge fields. So gauge fields in 3+1D, this is conceptually a little bit more challenging. The main reason it's more challenging is actually this fact. It's that the gauge interactions are marginal in 3+1D. However, there are some interesting ideas that people have for how you might be able to get around that. And I can just give you a toy example with something that's like QCD. So let's say QCD lives here. This is in the IR theory that we're interested in. And one option is starting from, let's say, free gluons, for example, and free quarks, and then turning on an interaction. Okay, and this is a marginal interaction that kind of runs down this way. You know, the coupling constant in 4D is dimensionless for QCD. Another option is starting over here at some other UV CFT that we understand. So this could be something like a Banks-Zaks fixed point, where I have some large number of flavors of quarks. Okay. Now I can perturb down to this way by adding, so let's say Banks-Zaks, something like this. So many colors, many flavors. And now I can perturb down by adding some masses to a bunch of fermions and maybe some Higgs field or something like that to break some of the symmetry. These interactions can all be relevant, which makes this flow very fast. The price you pay is you need to be able to compute this CFT data very well. And so there are kind of different techniques that people have talked about for how to do this. You know, this is open and ongoing work.
Oh, but Banks-Zaks fixed point, it's a conformal point, right? And so if you're far away in energy, then your mass term you can forget about the mass term. But when you start approaching the mass term, you immediately will lose conformal regime.
No,
and
that's
you
the
are
point.
back
Yeah.
to strongly coupled QCD.
Yes, but
Young Mills, not even QCD. Young
no,
Mills, because
yes.
all quarks can be integrated out, and the mass will play the role of MUV. The mass term will play the role of the UV cutoff for this Young Mills theory.
Good. I understand. What I'm saying is the tool here that we needed to like, what we did was we needed to discretize our Hilbert space and then diagonalize that, which means we needed to be able to construct this sort of numerical matrix. Saying that numerical matrix data that we construct.
But I don't understand why you need this part of the curve which goes above in energy or in distances, above the mass term.
Because this, I might hope I can calculate exactly.
Yeah, but this piece from Banks-Zaks in the extreme infrared.
What I'm saying is the
mass
UV
term
flow.
is totally irrelevant because it's a different
Yes,
dynamic.
but I can compute it. So the UV, the RG flow from the UV to the IR, this is what these truncation techniques can do. This is effectively like what you're doing when you do these truncation techniques.
Okay.
And so this is the part I'm saying, okay, I want a short flow. And I also want like calculable data up here. And here I have maybe easily calculable data, but the flow is very long. Here I might be able to get a shorter flow, but data might be harder to calculate.
These are two distinct theories on your
No,
trajectory.
these are, but they flow to the same theory in the IR.
The left trajectory.
I'm not adding, sorry. I'm not adding mass to all fermions. I'm adding mass only to some of the fermions, right? So I'm saying,
Okay, then you may drop them out from the very beginning. If you add up,
He wants to start with something he can calculate.
right.
He starts with something he can calculate.
yeah, but
and he
it's
wants-
a different theory, it's conformal theory.
Yeah, but he wants to connect them. He can-
But it's not possible because
Yeah,
in
it's
conformal
possible.
theory, there is no scale.
But he's
where you
breaking
can-
the conformal.
Huh?
He's breaking the conformal symmetry by adding. these
Yeah,
mass-
when you break the conformal symmetry and you are below the mass terms,
Right.
then you switch to a different phase, which is not analytically continued. It's a phase transition from conformal theory to confining theory. How can you analytically continue from the phase transition? That's the whole point
Well,
That's
this
the
is
whole
kind of the
point of-
question.
of a phase transition. It's presumably first order phase transition from conformal regime to confining regime.
Okay, so if you really,
How does it help you if it is first, even if it is second order phase transition? Whatever you calculate above them has nothing to do with whatever you calculate below. It's two distinct phases.
good. So the way that you would worry that this concern manifests itself in truncation.
Okay, you know, we're discussing empty space because you haven't done that.
Yes,
What you suggest, nobody have done that.
Yes,
Not
I
only
agree.
you. And I bet nobody will be successful on this way.
that may be, right? I'm trying to give you possible roadmaps for like, things that one can try to
This
do.
roadmap costs nothing because it's roadmap nowhere. Otherwise, it have been already used by many smart people who knew about this Banks-Zaks fixed point for not even for years, for decades.
Right. The leap forward that is being done here is not a leap forward in understanding this. This is something that's well known. I totally agree.
This
The
is
leap
a phase
forward,
transition on this. It's not a smooth road. It's not a smooth road. These are two distinct phases. The upper phase is well understood. QCD near the Banks-Zaks point becomes a very simple theory, conformal. You can use conformal properties for correlators, for whatever. It doesn't have a mass gap even. It doesn't have a mass gap, okay? And you want to pass from this phase, conformal, to the fully confining phase.
yes. So
When you do it, you come here and tell me that you did it. Otherwise, it's nothing.
okay,
I can promise you, to become as rich as I don't know, Bill Gates or whatever, but it's pure promise, Many
Yes,
people try,
right, so-
but it's pure.
So that's why this is at the end of the talk where I talk about, future directions, not at the beginning of the talk. Okay,
So I think, Misha, I think you want to prove that, but I think you cannot prove that. You can just
Right,
check
correct.
numerical
Yes, yeah.
correlations.
Okay, so with that, I'll conclude. I thank people for the attention and the very engaged, the high engagement. It's more engagement than I usually get. I'll summarize in the following way. The goal of today was to provide kind of a closed recipe, at least towards a closed recipe for computing scattering amplitudes in some strongly coupled field theory. Basically, a different way of doing this than probably you have seen before. My summary, I give this little emoji summary. So I have some very sharp, pointy object with poles. It's very hard to calculate, but I can rewrite him in terms of two very smooth objects that are very happy. One with cat ears and one with a little birthday hat. The true test of this that we just did was faithfully reproducing features of this ON model. All the results that I just showed you were done here. It didn't take very long. The kind of future directions that we want to explore are some of the ones that I've already told you, incorporating fermions, things like this. Also really studying bound states. I'd say that's a direction that's very accessible to us. It's accessible in 2+1D. And so this is something that I think will shed a lot of light on how to get closer to a realistic theory. And finally, we saw that the full analytic structure of these amplitudes is accessible. And this is kind of nice both for formal understanding and also possibly in the future for picking out with a higher degree of precision specific properties of resonances or things like this. Okay, with that, I thank you guys for the attention, and I'll take any last questions you have. I'm also happy to talk offline about technical details because there are many.
Yeah, do we have any other questions for Jay?
So is this technique generalizable to multi-particle scattering, for example, to n for
Yes.
large n, but not necessarily large couple?
Well, good. So certainly, like the kind of formulas that I wrote down are very generalizable. So effectively, that's you want to generalize formulas like this, right? So 2 to n particle scattering would have additional intermediate field, and so you'll have additional factors of j and j prime. All of those correlators are computable. You just need to you have more correlators to compute, so it gets more computationally challenging. If you're asking about doing some process like at the LHC where you want to have 2 to n where n is very large, I suspect that's rarely the best computational route to get there. I suspect like for example, I do not think that the way you should think about doing this is think about having 2 protons come in and then go to all of the mess of hadrons that come out. I think you should probably think of this as much better for computing 2 protons come in and we're going to the first stage of some first pions or something, and then those pions decay, or some first excited resonance, and then that resonance decays or something like that. I would still say that if you want to do that process, you're better exploiting the usual amplitude factorization you get for LHC type amplitudes.
Yeah, I think for weak coupling, still our normal perturbation theories states are still the more promising basis.
Yes,
Coupling, but there are many particles and the particle lambda m can be large, right?
Yeah,
I just want to say that.
So you want to say Higgs boson.
that's a good question, but I don't see the connection to this.
I suspect it's not the best way, just because
There are other methods.
yeah, it's not that this is not going to work. It's that the thing that was limiting my convergence here, my 1% or things that I was showing you, right? This is in some sense how many states I'm able to include in my basis. And if I'm working in an area where I want to include 100 particle states, that's a very large basis of states that I need to include. And so
it takes you 10 seconds to generate this plot, right? So
there's a lot of room to scale up, but there's also a lot of scaling up that you need to do to go from 2 to 100, right? And that probably scales poorly, right? Like there's sort of factorially many things at 100 particle states. That a lot of the leverage you're getting here, by the way, is effectively like this is a variational technique that people are doing, these truncation techniques. You're trying to come up with good approximations to what you think the low energy states of the theory look like. And a lot of the leverage you're getting is that by and large, even at very strong coupling, your guesses of what those states look like aren't horrible. Like there genuinely is meaning to the statement that the proton kind of looks like two up quarks and a down quark. There's a lot of other stuff in there, but actually it's relatively rare to find a proton that's looking like 10,000 up quarks, 10,000 U-bar quarks, and two up quarks and a down quark, right? Like your low energy guesses for what those states look like, even at strong coupling, in many theories seem to be decent. And so these methods tend to converge quite quickly.
Well, it depends on really the question you ask, right? So you talk to Zen and he will tell you that if you go to very high energy, right, the proton may contain thousands of gluons.
Good,
right?
good.
Because the structure function grows on that.
Good. I will go to very, very high energy when I have figured out the low energies. There are just other techniques that are going to be
Can
very
I
good.
take a look at the insertion you made, the expression of the insertion you made of this calculation? Just we
Like
just want to see the expression.
this kind of expression,
Yeah. What's the state you insert?
this state.
But it's a bit abstract to me.
Good. So what have I done here? I've maybe I just kind of
Yeah,
sketch.
abstractly you are using momentum and labeling the.
Yeah. So
But I need to see an expression. What's the expression?
good. So I've written down some free theory states that I understand. So I've taken some collection of free theory states. Let's label them by whatever, some index I at some particular momentum, something like this. So these are states that look like, two free massless particles with some particular spin or something like that. Okay. So I've written down a whole collection of these. That is those truncation parameters. So there's
massless free particle, massive.
massless because I'm computing starting from a CFT.
Okay, from a field massless particle, I have ways to assemble the momentum and the spin. I'm just trying to.
Effectively, yes.
I'm just trying to.
So I'm saying I've written down, like 6,000 of these guys, something. Now for each of these guys with every other guy, phi j at the same momentum, the momentum label is the same. I compute sort of the full theory Hamiltonian. So this is really saying I compute the deformation because the free theory Hamiltonian is trivial. These are diagonal and the free theory Hamiltonian. So this is saying I compute like the overlap of these with the intermediate mass state, and then the overlap of these with the intermediate the intermediate interaction, 5 to the 4th interaction. That gives me a big matrix, like 6,000 by 6,000 matrix, something like this. I diagonalize that matrix. The output from that are these states that I write down. So I have these states, they're like this, and my output is this number, their eigenvalue, and some sum, over J of someCij's of these free states that I started with. Okay, so all of these guys, this is free CFT states.
Okay,
so this
CFT free particle CFT states is a good basis to insert in the system. So you decide to carry out the calculation.
But there's it is really important that you do this diagonalization because you need this to do these kinematic integrals, right? To get things like this. That's only because they're exact eigenstates of the full theory. So you can use translation, the translation operators and things like that on them, right? So it's very important that they look like this. But the actual data that you need is effectively CFT 3-point functions, right? It's external state that sits here, external state that sits there, and in the middle an operator. So it's some CFT 3-point function that goes here, CFT, sorry, full theory like diagonalized eigenvalues. So, yes.
Why do you need to take the theory to be massless? Like, why does it need to be a CFT? Why would a massive free theory not be good enough?
Effectively because it's much easier to compute. Like a CFT, I generally have more control over what's going on. You're correct. Like I could deform from a massive theory. That's not a problem. But like kind of in general, the easiest tools I have to compute things are when I have a lot of control over the theory, in the CFT. But yes, I could have I may have been able to reformulate this in a way where the mass term, like the theory with the mass term is exactly solvable, right? But the 3-point functions of a massive state with the interaction with another massive state, those may not be as easily solvable. I'd have to think. I suspect in this case, you could you could solve that actually, roughly because of this thing that I told you, that the mass term and the interaction term tend to lead to different off-diagonal elements of this big matrix. In more complicated theories, that's not the case. So for example, in phi to the 4th theory, like that's basically because there's some ON symmetry that's protecting certain matrix elements. If I were working in phi to the 4th theory, that's not true anymore. And so then I think you wouldn't be able to do that very easily. Yeah. Okay.
Can you use this technique to compute a lifetime instead?
Yeah, I could have a decay rate completely fine. Yes, a decay rate would look like something like a 1 to 2 instead of a 2 to 2. In fact, decay rate would have been, if anything, easier because I would have had one fewer J floating around.
I think maybe we can thank Jed now. And if you want to ask us more questions, just send me a
I heard you guys brought snow just for me. Appreciate the cold welcome.